talk will be graph processing in Python. I introduce you to Lindberg. Give him a warm round of applause. Yeah.
All right, everyone. I am excited to talk to you today. I'd like to spend about let's make sure that the volume is right so that you can both hear me and I don't make your ears bleed. So can you all hear me? Excellent. All right. For those of you who don't know me, I have a deep and abiding love of graphs. I use them all the time in various ways. And it's come to my attention that this is something that a lot of people don't have a lot of experience with. They don't really see the joy of playing connect the dots that is graph processing and graph theory. And so yesterday, or a couple days ago, I taught a tutorial about, sort of initial modeling. This is in some ways a continuation of that. Things that you can do when you have a graph and when you start to apply it. And so a lot of these things I've got visualizations for. Some of them are easier to see than others, but I thought it would be at least fun so that we could do it. So let's start out by talking just for a second about graphs. When you've got a graph, you can model anything as a graph. Graphs are a universal data type. You can model anything else using a graph. But the fact is that it isn't always a good idea to, even though graphs are a fantastic hammer, they're not always the right tool for every single thing. When you want to use a graph is when you have a relationship between two facts or two people or two things, and you want to express some kind of relationship between them. If you don't have this relationship, then graphs are probably not a good fit. And so if you identify the nodes, what the facts or the objects or the items that you really want to focus on, and you identify the relationships that you want to bring out between these facts or these items, then that's when you can start to do interesting things with graphs, and that's when you start to get some meaning out of them. So I'm going to talk about a couple different problems where, just for fun, I applied graph processing to learn some things about Python. Now, this is obviously our favorite language, or at least it's mine. I assume it's up there for most of you because, well, you're here. For each one of these things, I'm going to talk about 5 different things. The first is I'm going to talk about the problem. What are the questions that we're trying to solve? What are we trying to actually do? Second, I'm going to talk about the model. How do you lower that into a graph representation? This is really about that question that I was saying earlier. What are your nodes? What are your arcs? What are your relationships? Then I'm going to show you a few snippets of the code where, both in terms of building the graph and then in terms of a little bit of the analysis, I didn't have enough time to I tried putting all the code on the slides. It didn't fit. It wasn't legible. And so I'm just showing you some of these snippets. I've got this visualization of the graph so you can see it, and sometimes it takes a minute to settle down, but we'll talk about some of the features of the graph, and then we'll talk about some of the ways in which we were able to answer the question and actually do some of this analysis and find out some of the solutions to our problem. So I'm going to go in a slightly different order than I had on the thing, but I'm going to touch the same 3 topics. The first one, I'm going to talk about Python Dev. How many people here read Python Dev? A fair number. So what you do is sometimes it's really interesting to understand who talks to whom. If you're trying to get something done, who are the people that you really want to get in touch with? Are there particular communities that tend to talk to each other? Are there cliques where, these people are really in tight? Are there connectors? If anyone's heard of Malcolm Gladwell's book, Blink, I believe, where he talks about these super connectors, or these people who, hey, they're the ones that if you get the message to them and they tweet it out to everybody or they email it to everybody, all of a sudden everybody knows about it. So do we have these sorts of things in Python dev? So in terms of the model, well, I've already given you the answer. What we're going to do is we're going to represent people as the nodes because we really want to know the questions we want to ask are about people. And then we're going to, because we're looking at a mailing list, the arcs are going to represent responded to. It's a directional arc in this case, meaning that sometimes if I respond to a person, particularly on a mailing list where anyone can read it and anyone can respond, there's more of an indication of interest when there's a response to than simply sending it out. So that is going to be our model, and that's how we're going to look at Python dev. Now, in order to get to this, so let's look for a minute at the code. What I did is I downloaded all of 2011, the various archives of Python dev. And then taking this, I went through and I built a tree. And for each one of these topics, for every time someone sent out something, I looked at, okay, here are all the people that responded. Then for each one of those, I looked at, here are the people who responded to them, and all the way down recursively to the end. So if you'll notice, I've got this build graph function here. Actually, it's easier to point to here. So network X, I'm using network X, a digraph, that's for a directional graph. So what I did is I had a topic and I had a person. So I got all the responses, and I got all the people that made responses. And then for each responder, I added a node back saying this person responded to the original person. And then I did it recursively all the way down for every topic over 2011. So that gets me my graph. So what do you do from there? Well, one of the neat things that you can do with graphs is you can talk about centrality. Centrality that has various definitions, and there are various ways in which you can be central. But intuitively, what it means is that the people who are more central tend to connect others. These are the super connectors. These are the people who are most active in the mailing list. These are the people who really tie all everything together. And so what you have here, when you're looking through the code, I went through and I found the centrality based upon, I created a dict of the centrality score via various measures. Between this centrality, these people are between a certain number of nodes, eigenvector centrality, I forget the other one that I used. And so then I created a dict where you mapped the person to how central they were as a floating point score. And then I returned the ones that I sorted that by the score, and I returned the ones that were the most central that had the highest score. So I was able to do this. So what does my graph look like? This is Python dev. Now a couple of interesting things about this is that, sorry, it floats around a little bit, so we're cut off a little bit. One thing you'll notice about this, just sort of intrinsically and intuitively, is that you tend to have sort of two orders of people in Python dev. The first is you tend to have a tight core of people who have a high level of interconnection with each other. Remember, each one of those dots is an individual contributor. There were 346 people who contributed over 2011. Then you have a ring of other people who are only interested, who only participated in one or two interactions, and they are sort of this ring of lurkers, perhaps, people who are interested in a particular bug or a particular issue, something like that. I looked at I looked at various community detections, and I found out that it really matches what you might think when you're looking at this graph. There's one fairly tight-knit community right in the beginning, and then you have a few other smaller communities around the edge. So when we're looking at this, and so there wasn't really some distinct cliques, as they're called, where here are people who really own this, and here are people who really own that. There was a lot of give and take, or back and forth among all the major contributors to Python Dev. But and it divided into about, there were about 150 people who were in the core, and then the secondary group was the rest of the 200. Now, when you're looking at centrality, who do you think was the most active? Who were these super connectors? Who were you most likely to receive an email from? Guess. Guido? Okay, we got one vote for Guido. Who else? Raymond Hedinger. Martin Van Loos. Anyone else? Tim Peters. No one's got it yet. Nick, getting close. Antoine Petro was the most central person on Python Dev last year. He narrowly beat out Nick Coughlin to, you were more likely, if you posted to Python Dev, to get a response from Antoine than from anybody else. He had a centrality score of 0.2, and Nick Coughlin had like 0.19, which when you go on which is incredibly high. Interestingly, Guido actually came in about 5th. And a couple other people there, Barry Warsaw was fairly active, Raymond Hedinger was active, but these three were the ones that were most active overall. So that is our anecdote number 1. Anecdote number 2 is, what did people talk about? Now, the way in which you can think about this is, if you ever needed to build a social network and you had a bunch of people who had bought stuff, like say you were Amazon and you say, people who bought this also bought that. You can infer things about people when you have similar topics of interest. So when we're looking at Python Dev, what are people talking about? So who was the most likely to comment on on various topics? Now, let's think about our representation. Here we had a model based on 2 different things. Instead of just thinking about people as our nodes, we have actually people and topics, because the relationship is people commented on various topics. And then we can look at people who commented on similar things and had a similar pattern of commenting in order to say, hey, 2 people who have a similar pattern of commenting are probably going to be similar in terms of their overall interest. We can also look at a particular topic and say, who are the people who are most likely to be interested in this particular topic? If there was a community that focused on a particular subject, who would be the people who would be most likely to be in that community? One thing about this is that there are certain things that just are so popular that everybody tends to comment on them. They're not good discriminators. There are other things that are so minor that not many people comment on them, and so they also tend to be not good discriminators. So what we did is we filtered out both the most common and the most rare, and we had this group in the middle. So let's focus for a minute and let's look at the code. This time, you'll notice that I'm using a graph instead of a directional graph, because we actually want to model things both ways. There's meaning both in terms of saying that a person commented on a topic and the topic was relevant to that person. And so because there's a bidirectional relationship that we're trying to capture, we are not forcing a direction on our meaning. Instead, we're saying it can go either way. The second thing is that, so we went through and we parsed all of the messages, and we said, okay, what's the the person, what's the topic. Now, in doing this, I actually pulled out a little bit of natural language processing to pull out the most common words and bigrams and things like that. And I condensed them down, and so I did a little bit of massaging on the topics in order to get them into something, and I filtered out stop words and did sort of things. But ultimately, I had this thing where I parsed the message, and I got, here was the person who made this message, and here were the topics that were generally treated in it. And especially the overall subject of the message, I treated as especially significant. You'll notice that when I build my graph, I added a type identifier. It's a little bit of metadata to the node. The metadata just allowed me to filter and say, hey, these things are nodes, these things are people, and separate that when I'm doing my analysis. And then I added an edge between the two. So then, there's a natural sort of mapping between the number of the degree of a particular node and how popular it is and what you're doing. And so the degree of a node is basically the number of edges that you have going in and out of it. If something has high degree in this particular model, it's going to be very popular. Or if it's a topic that has a high degree, it is very popular because it connects a lot of people. If it is a person that has high degree, then it is a person who comments on many topics. And you can see how that sort of overall that the meaning can go either way depending on the interpretation you put on your nodes and on your arcs. One other thing that you can do, which was a lot of fun, is to identify subgraphs. Now, a subgraph is where you find two graphs that are the same shape. And what you did is you looked at people and you said, okay, what are the topics that this person is interested in? And they would be interested in topics A, B, C, and D. And then, all right, is there anybody else that shares this same subgraph? I.e., if I swap out this person, they're also interested in A, B, C, and D. And there is relatively large overlap between the degree of person A and person B. If person A and person B have isomorphic subgraphs, and they are, or they have similar subgraphs, where one is a subgraph of the other, and they are similar in degree, then we can say that these people have a similar spectrum of interests. And so they would tend to be in the same community. All right, so let's take a look at it. Now this one takes a minute to settle down. Unfortunately, like I said, it floats around a little bit. This is, I think, one of the most fascinating things. Here you see this central core are the people. And what you see are the various topics in rings of significance. So there are, what you see in the central ring are the most popular topics on Python Dev, then followed by, they're a little less defined than that first ring, but a second, third, and fourth ring of decreasing importance in topics as measured by the number of people who are interested in them. And so when you were looking at this is, again, just a visualization to help you sort of think through that and get an intuitive sense of what you were looking at when you were doing the math. But that's what the graph is. And then you can imagine that we would take one of those, here, I might even be able to, So you see that this particular person has those connections, if you can see him right there. And so what I would be able to do is find someone who has a similar set of connections. So, okay, we're floating away. Oh, well. Okay, so the question is, what did we learn? Did we find out anything about Python Dev? Well, there we learned that there were 122 significant topics over the past year, and I've listed them for you. For those who read Python Dev occasionally, you'll probably recognize some of these topics. I mean, it's not surprising that we see a lot of interest in 3.2 and Python 3 in general. You see a discussion here about what should the symlink be for Python 2 versus Python 3. When do we actually move this? We have some discussion of the Python Summit that went on here at PyCon. This is an interesting one. There was a security vulnerability not too long ago that resulted from predictable hash collisions, and it resulted in a number of security releases of Python. So that was a major source of communication. By the way, these are roughly in order of frequency. You see, you had the packaging was a subject of some discussion. You had a lot of discussion what goes into the standard lib. You had C types. You had PEP 393. All these sorts of things were major topics of discussion over the past year. So the question is, what did we learn? Well, one of the things that we wanted to learn about is who is most likely to talk about a particular topic or set of topics. And I didn't do the reveal, but these are the people who are most likely to speak up or to comment when someone talked about optimization. And when you think about it, that's not too surprising. Do all of you know who these three people are? What's interesting is that they tend to take very different philosophical approaches to optimization. If you know sort of their personalities and the way in which they approach things. But yet, this was definitely a topic of interest and a topic in common between these three. So that is number 2. Number 3. There. Evidently, we've got an issue. Okay. Number 3 is a topic of interest to me. In my day job, I'm a lawyer. And so I track a lot of stuff about law. And one of the things that is, frankly, a minor source of irritation to me is Python's license. Not necessarily the license that the new code is released under, but if you look at the Python license that you receive, it's what I sometimes call a stack of pancakes license, i.e. there's a license at the bottom, a license at the next level up, license. I've got 5. Okay. It's this stack of pancakes license. And I'd really like to say, you know what? Do we really have any old code that is covered by that old license from Python.9 way back when? Well, it turns out by analyzing the change in graphs over time, you can actually answer this question. Now, this takes a little bit of thinking. And so what we did is, first of all, subversion blame is so for these, subversion blame was my friend. So I was able to go through and I checked out the Python full history and updated it with the current things. And then each node, I didn't do it for the entire thing. I did it for everything under the Python subdirectory because otherwise I was getting multi-gigabyte files and it just was taking too long. So each one gave me a 6 megabyte file that I went to parse through. And what I did is I represented each node as a file, and the relationships between these files would have the same license as, are co-licensed with. And the way that you would be able to tell is by noting when this was last changed. Now, is this foolproof? No, you would actually need to do some more legal analysis. But as a first cut, you could say, hey, if something was released in 1998 and was not updated, has not been updated since, then we know at minimum that was under the license from CNRI. If something has been updated in 2010, then the re-release, we would need to see the connections and the legal questions and whatever, but at least as a first cut, we could say that piece of code is co-licensed under the PSF license. So then, with doing that, we created a series of graphs where each graph marked a set of years, and we looked at the co-licensed groups and the clusters. Now, this one I don't have a visualization for because analyzing the change in graphs over time is very difficult to sort of visualize. But what you can imagine is these different sort of clusters changing size, and so you would have, when you started out in the 1990s, everything was under the CWI license. Then that started getting smaller as code moved from one cluster into the CNRI cluster. And it was under those two clusters. And then there was a blip with the BOpen cluster. And then it moved on to the PSF cluster. And stuff has been consistently moving into the PSF cluster from these other clusters over time. And so you can imagine that movement and these bubbles sort of growing and shrinking over time. So what did I learn? I learned that there is still approximately 110 lines of code that still came out of the 1990 release. It goes back to the very earliest commit of Python in the current, as of a couple days ago, checkout of Python. That said, most of it, 2010 was a massive year for development. Not surprising considering all the things that went on in Python 3 and the development of Python 3 and releasing it and refactoring the I/O system, etc., and the object model. You tended to get these basic graphs, but there are certain files which we can identify which ended up being, hey, this either came out earlier or we have been able to track a change to every line of source in this file in order to say, you know what, at a first blush, this is something that is, here's something that is going to be probably licensed under this new license. Those are the three things that I had sort of prepared. I've got, how much time have I got? 2 minutes. Have any questions?
What was the graphing package you were using when you were doing the demo?
I was doing an export from network X to d3.js. It's fantastically powerful. It also has a bit of a learning curve, but it's worth using. Other questions? There was one down here.
I was just wondering, so when you have a big graph, you have a whole bunch of fun dots and just tangle lines. Do you have favorite alternate ways of representing the graph?
Okay, the question was, are there alternate ways of representing a graph? One of the ways in which you can do that is by coloring the graph according to clustering it and grouping it depending on different attributes that you put into it, and then clustering it according to those attributes. There are a couple of great packages. One is called Gephi. The other one's called Nodebox. Nodebox is for OS X only, and those are really fun for playing with graphs and doing a number of different visualizations. Other questions? Do I have a blog? Not yet, but that's on the to-do list.
So you didn't touch too much on the subgraph.
Okay, a subgraph is defined as, a subgraph is very similar to the idea of a set, where a subgraph is defined as, wow, you know what? We'll talk. Anyway, thank you very much.